Hello everyone. Today I'm going to follow up with my last video on wireless power transfer. In this video, I'll mainly focus on analysis. In the first part, in one test, I showed that as the coil separation was decreasing, initially a load or a light bulb connected at the secondary coil starts to get brighter and brighter, and at some certain close distance it has started to dim. So why is this thing happening? I'll try to explain that. I'll also show some data like power, efficiency and current, and there will be some interesting and useful formulas if anyone wishes to do some calculations. In the third part, I'll show some practical circuit to use the wirelessly transferred power, such as charging a cell phone or charging a battery pack, etc. In my last video, I mentioned that in a wireless power transfer system, resonance is utilized to efficiently transfer power over a distance of few centimeters to a few meters. The primary coil is powered by an AC source with a capacitor in series. At resonance, the current goes higher and higher magnetic flux is produced. The secondary coil picks up some of the flux and a voltage is induced across the coil. If the secondary circuit is tuned to the same resonant frequency, maximum power transfer can be achieved. If the inductance of the coil on the primary side is L1, added capacitance is C1, and the circuit resistance is R1, the resonant frequency is expressed as 1 over 2s pi root over LC, L1 C1. If on the secondary side the coil inductance and the added capacitance have the same values as that of the primary side, the secondary side is also tuned to the same frequency. As the magnetic flux created by the primary coil current induces voltage on the secondary coil, one factor comes into effect, that is mutual inductance, or M. M is defined as the root over K times L1 L2, where K is the coupling coefficient. K is a measure of how well the flux is linked to the two coils. K equals 1 means 100% flux is linked, and which happens to the transformer. K equals 0 means there is no flux linkage at all. Now if the current through the primary circuit is I1, the AC circuit equation for the primary side and the secondary side can be written by these two equations. For the primary side, V is the source voltage, I1 R1 is the drop across the resistor R, and this is the voltage drop across the capacitor, and the term J omega C1, 1 over J omega C1 is called the capacitive reactance. It is also expressed as XC1, and the third term, there is the I1 times J omega L1 is the inductive reactance by the coil, and also expressed as I1 XL1, and the fourth term, that is the I2 J omega M, that is the mutual effect of mutual inductance. And on the secondary side, you see there is no source. The induced voltage across the coil is the only source. So I1 J omega M is the voltage across the coil, and the other term are the same as that of the primary side. There is the inductive reactance and capacitive reactance, and this is the voltage drop across the secondary circuit resistance or load resistance. And at resonance, this inductive reactance and the capacitive reactance of both the circuits are equal. When AC voltage is applied across an inductor, voltage leads the current by 90 degrees, and for a capacitor the opposite thing happens. Voltage lags the current by 90 degrees. So at resonance, both on the primary and the secondary side, the capacitive reactance and inductive reactance cancel each other. Now the equations become simplified at resonance. These two terms are cancelled, so I1 j omega m equals I2 R2, and on the primary side V equals the fourth terms as mentioned before, so these two are cancelled, so it becomes simplified as V I1 R1 minus I2 j omega m. So we can replace this I2 with this one, and we finally reach this equation. Now for this simplified equation, I am explaining each term once again. M is the mutual inductance, can be expressed by this equation, K times root over L1 L2, and R2 is the coil plus the resistance of the secondary circuit or load resistance, and L1 and L2 both are 155 microhenry, and the R1 is the primary side coil wiring resistance, and V is the applied voltage, and omega is the resonant frequency. It is the angular frequency, so if we know the frequency, then we can find out omega, and using the first equation we can find out the current through the on the primary side, and using the another equation I2, the secondary current can easily be found. Now as we know that M depends on K, which in turn depends on the coil separation, as the coil separation increases, M decreases, and the primary and the secondary current behaves like this. M is coil separation increases, M decreases, and the I1 primary current goes up and the secondary current will go down, and the power dissipated by the load resistance can be expressed by I2 R2, I2 square R2. This slide shows a very important relation. This is the output power to the input power ratio. P2 by P1 equals omega square K square L1 L2 divided by R1 R2. And as we know that as coil separation increases, the value of K decreases. So to counter that, what we have here for the wireless power transfer system, we can increase the omega and we can decrease the primary side resistance. R2 is the load resistance. It depends on our demand. So we have to rely mostly on R1 and frequency omega and L1 and L2. So our choice of frequency is very much dependent on L1 and L2. So we can mostly manipulate omega square, omega and R1. So as the frequency goes up, another effect becomes very important, that is called skin effect. Higher the frequency, the electrons move to the surface of the wire, so resistance go higher. So very much higher frequency will not give us any advantage. That's why several hundred kilohertz or few megahertz is the best choice for wireless power transfer. The experimental setup is shown here for various measurements. I am going to use DC power supply meters to measure the input current and voltage. There will be some loss in the DC to AC converter though. On the secondary side, I am using a DC voltmeter and an ammeter with the load to measure the output current and voltage. Here is the photo of the experimental setup. Two different lamps are used as loads. One is a 12-volt auto lamp and the other one is a 115-volt AC lamp. Both are incandescent lamps. I measured the resistance of these loads. If you try to measure resistance of this type of lamps using ordinary ohm meter, you will measure very low resistance. When these lamps are powered up, the wire inside gets heated up and the resistance goes higher. For instance, at full power, the 12-volt lamp will have resistance approximately 6 ohm. On the other hand, 115-volt lamp will have nearly 220 ohms. As I am not using the full power, I may consider 3 ohm for the 12-volt lamp and 150 ohm for the 115-volt lamp. First, the 12-volt lamp was connected to the secondary side. The input and output current with the coil separation is shown. You can see the input current when the separation is 15 centimeter is 3 amp, because the power supply we can adjust the constant current mode to be at 3 amp, so it remains 3 amp. So as the coil separation is decreased, the current goes down like that. And on the secondary side, what happens at 15 centimeter, a certain amount of current is flowing. As the coil separation is decreased, the current goes up and it reaches a peak at around 1.5 amp, around at 7 centimeter coil separation, and then it starts to decrease as the coil separation goes down. This slide shows the input power and the output power and efficiency. As you can see, the efficiency reaches peak at 50% when the coil separation is around 5 centimeters. For the 115-volt lamp as a load on the secondary side, as the coil separation is decreased, the lamp current increases monotonically. No peak in the middle is seen. Efficiency also increases with decreasing coil separation, and maximum efficiency found was 35% for a minimum separation of 2.5 centimeters. Before going into the analysis of two different situations for these two different types of loads, I am bringing coupling coefficient versus distance plot, which I showed in my previous video. The spreadsheet for the plot also gives me an empirical formula for the distance versus k. K equals 1.52 times d to the power 1.463. Using the value of k, we can get the value of m at various distance, and we are then able to calculate the input and output or the secondary current. Now we are able to calculate the input, output current, power and efficiency. Calculated plot of the output current or the secondary current is shown. For a load of 6 ohm, we can see there is a peak at coil separation around 7 centimeter. Then closer it gets, the current starts to fall. For the 3 ohm load, the result is similar. For 50 ohm load, we do not see such a peak in the middle. The situation is again shown here. For 6 ohm load, as the separation is decreased, the secondary current starts to increase and reaches peak and then falls. The situation is shown here for 150 ohm load. As the coil separation is decreased, the current goes higher and higher. We can also explain wireless power transfer under various situations using simulation. For simulation, I am using LT Spice. As it is free, anybody can download it to use. So for the primary circuit, I measure the coil resistance, that is which is 0.4 ohm, and its inductance is 155 microhenry. I am using C1 0.33 microfarad, and the circuit resistance or the other wiring resistance I consider it to be 0.2 ohm. On the secondary side, the load resistance, I use two types of loads, 6 ohm and 150 ohm. Capacitance is the same as that of the primary one, 0.33 microfarad, and the coil inductance is 155 microhenry and its resistance is 0.4 ohm. First, let us see what happens with the 6 ohm load, and this is the schematic drawn with the LT spice, and the value of K, that is the coupling coefficient, varies from 0.1 to 0.4 with a separation of 0.1, and this is the primary coil, secondary coil, and this is the load, and this is AC. I consider it to be 13 volt. Here is the simulated result. K equals 0.1 means the coil separation is 7 centimeter. Current peaks at 22.2 kilohertz, which is the resonant frequency. For K equals 0.4 means coil separation is around 2.5 centimeter. At this point, the current is decreased. Another interesting thing to be noted is that closer the distance, a single peak splits into two, and this is called bifurcation. And for a wireless power transfer system, this kind of bifurcation is avoided by optimizing the distance or the load resistance. This is the schematic for the simulation with 150 ohm load. At the secondary, the variation of K is the same as before. For the 150 ohm load, the situation is different. For K equal 0.1 to 0.4, output current is the same in the frequency range of interest. Only the current goes higher and higher with increasing K or decreasing separation. So far we learned that in a wireless power transfer system, it is important to maintain low impedance in the primary and the secondary circuit. Load also plays a significant role. If the load resistance is low, transfer efficiency is good up to certain coil separation. Then due to bifurcation, at closer distance, efficiency falls. For higher resistance load, efficiency becomes poor. Considering all these things, we have to choose a DC to DC converter to optimize the operation, which can give constant DC voltage of our interest. In the next video, we can see practical use of wirelessly transferred power in battery charging and cell phone charging. I use two different types of lamps for the load at the secondary coil. One is a 12 volt auto lamp, and I'm trying to measure the resistance of this lamp. And if I try to measure the resistance with a ordinary ohm meter, resistance is very low, and you can see it is nearly 0.5 ohm. But when current starts to flow through that, the wire inside gets heated up and the resistance value increase. Now I am taking the 115 volt 60 watt incandescent lamp, and you can see the wire inside, and if I measure the resistance as before, you can see that it is around 24 ohm, and the current flowing is almost a zero, very low current. So when it is connected to 115 volt AC, the resistance jumps to 220 ohm. So now I connected the 12 volt lamp at the secondary, and as you can see, the distance is getting closer and lamp is getting brighter. I'm measuring the voltage and current at the output, and at some certain distance you can see that the lamp gets dimmer. So I'll explain the situation later. And here I connected the 115 volt lamp at the output, and you can see the current and voltage at the output. So the distance is getting closer and current and voltage starts to increase, and I'm getting the data for the current and voltage from the meter. And when the distance is pretty close, nearly 1 centimeter apart, then you can see that it is the lamp is very bright indeed.